Feel free to ask questions if you have any right now. I'm just waiting for class to start and to see if anybody has any questions. Until then, feel free.
Hello, Mr. Younger.
Hello, Logan. How you doing?
Good, how are you?
Not too bad.
So, I actually ran into more problems about next semester taking 242, because I had some people tell me not true information about the whole thing, so everything has changed. So, I can't do the Zoom with you on Tuesdays and Thursdays because that pairs up with Miss R's Thursday night lab, which I can't do. So
Gotcha.
pretty much my only other option is to do your Monday and Wednesday lecture with your Wednesday morning lab. But then there's a problem with that because I have a Monday and Wednesday lecture at Eastern Shore Community College at 4:30. And the only way I'd be able to make both is if I left after the lab on Wednesday
Mm-hmm.
and like went to the Eastern Shore Community College and like joined a Zoom. But
Gotcha.
that's up to
Kind
you
of tight.
obviously, but that's just like
Yeah.
what I'm doing too.
Well, you can also do this, and we can do it off the books or on the books. You can actually, I can let you attend my day classes and then do my actual night classes on Zoom if you want. So you register for the night classes as if you're going to do everything night class, but then you take my day lab. So that's something I can work out with you. So if you sign up for it, just talk to me. And like I said, we have quote unquote 24 seats for lab, but that's not a fire marshal type number. So we can actually add more as long as we have the appropriate equipment and stuff like that. So I can let you attend. I think I've got two or three people already doing that. So you can certainly do that, or you can do the other way if you wanted it. I will work with you either way. I think it might be easier for you
Okay,
to
so
do the Zoom class at night and take the day lab.
Okay, so I would be able to do like the Wednesday morning lab with you and then still do the Tuesday and Thursday Zooms with you.
Mhm. Yeah, it just would
Okay,
you
well,
coming
that
to
would,
school 3 day, or you're doing my classes on Tuesday and Thursday, and then my lab on Wednesday. So that'll be a little different, but that's okay since two of them's online anyways.
okay, because yeah, that would work best to do the Tuesday and Thursday Zooms lectures and then the Wednesday morning lab. That would work a lot better.
Yeah, I might even see if there's a way we could maybe even break up, two separate labs or whatever or something. I have to talk to somebody, but if we get too many people that want to do that, then I'll have to do it. But I suspect there might be a couple people that would prefer to take the night lab, but I'm not sure because when you have it on different days, it's really hard to find somebody that wants to take a day class and a night lab if they're not on the same days a week. So, but yeah, I can definitely work with you. So don't worry too much about that. If not missing lecture is easier to happen when you take the night class, then by all means take the night class and we'll work out the lab scenario.
Okay, thank you so much.
You're welcome. And that's true for all my people. Like I said, I've got two or three people that are interested in doing it already. So anybody else have any questions or stuff going on?
Were you talking about attending your lab in the mornings next semester?
Yes. Yeah, because I have a night class like this one, but with 242, but I have a day class with 242 with lab. And some students are preferring to take the lab during the day instead of that night. And like I said, I've got two or three people so far that are interested in doing that. Maybe she's a fourth. But I could work out. I'm pushing the envelope. Once I start getting around four or five people, that's about as much as I can do. But there's always a chance that some fraction of them are going to drop anyways. So it might not be that bad even if I push it to five or six. So just, if that's something that has to happen, I will work with you to try to make it happen. And we'll just get some way to figure it out.
Okay.
Would that help you too, Jacob?
Yeah.
Cool. Yeah. So keep that in mind. I'm willing to work with you. We can do that. We don't necessarily have to do it officially, but if you actually have a class that interferes with the night lab, and that's the reason that you want to take the day lab, we'd actually have to do that officially, because you can't have something in SIS where it says you're at two classes at one time. So that one would have to be done officially on the books, whereas the other ones I could just do it unofficially. And there might even be a scenario where you could attend if Ms. Raskovic has a class or something at some other time, or someone else has a class at some other time that has a lab. You might be able to attend those, including, by the way, 202. We do the same labs for 202 as we do for 242. So between all that, we have some way of helping you. Okay.
Okay.
All right, so I guess we should go ahead and get started. It's 5:20. Oh, it's 5:23 already. Ooh, I'm late. Okay, so last time we finished up chapter 10, and we're jumping now into chapter 11. I do want to tell you that I just made 2 tests available to you guys. We haven't really taken a online test for chapters 7 and 8, which I think I called that test 6. I went ahead and made that and the practice test available, and I've given you till 15th, which is like Wednesday of next week, to get that done, if I remember correctly. And that shouldn't be too hard because you just finished taking a test that covered chapters 1 through 8. So hopefully that's not too big of a deal. But that gives you, like I said, all this weekend and then 3 or 4 days or 3 days next week. If that becomes a problem, let me know. I might even be able to extend it a little bit. But the main thing is the next test, which would be on chapters 9 and 10, that's due not this Sunday, but a week from Sunday. That's why I tried to push them, 3 or 4 days apart. So you got one on the 15th. That would be test 6 on 7 and 8. And then you got one on the 19th. That would be test 7 on 9 and 10. So just keep those in mind. They're already on there. The practice tests are already on there. If someone's having a problem with making it on the 15th or by the 15th, just let me know. I might be able to push it back. The main thing is I wanted to not necessarily have 2 tests due on the 19th. But that's harming you if I put the 15th there and you can't do it by the 15th. I'm perfectly willing to put on the 19th for that case. But like I said, I think y'all can do it, and it might be a little nicer for you to get it knocked out by Wednesday, and then you'll have another one on Sunday. So make sure y'all pay attention to that. Please don't miss all that good stuff. And we are starting chapter 11. And chapter 11, I thought I could do it all in one day, but that did not turn out to be the case today in my class and face-to-face. So that's probably not going to happen. So let me start off by telling you sort of the parallel story, if you will, with regards to conservation of angular momentum. So we told you when we were covering linear momentum, there is an actual parallel between linear momentum and angular momentum. I think I might have said it reversed a second ago, but the main thing is what I'm telling you is that there is a nice parallel between linear kinematics and rotational kinematics. And here's one example whenever the screen opens up. When we started studying linear momentum, I opened up with Newton's second law, and I expressed it in the way that Newton really did express it, which is the more general case. So when I say the total force, the summation of forces is equal to m times a, that's not technically the most correct form. In fact, if the mass is changing, that equation does not work. So really what it was is the summation of the forces is equal to dp dt, where P is defined to be mv. And that's just for one particle. For a system of particles, of course, P would be the total momentum, and that'd be m1 v1 plus m2 v2 plus m3 v3 plus for however many particles you have, and v is always a vector, as is P. So that's the case. But if the summation of the forces, well, I could have made an uglier F, I guess. Not sure I could have, but I could try. So if the summation of the forces is actually equal to the 0 vector, then we have dp dt is equal to the 0 vector, which you know from regular calculus, not vector calculus, that when a derivative is equal to 0, that means the function's a constant. So in this case, we say P equals a constant. And that's conservation of angular momentum. That's the whole thing in a nutshell. So that's conservation of linear momentum. And again, the importance there is not only for a particle, but more specifically for a system of particles, so that the total momentum of the system is zero. So in an exact analogy to that, we have the summation of the torques is equal to dl dt, and your book actually sort of does a reverse derivation of that and then says this is not technically correct, because what they start with is I omega. So the summation of torques equals I omega, or excuse me, I alpha. And then we put alpha is d omega over dt. And then we say, well, let's pull I inside, which you could technically only do if I, the moment of inertia, is a constant. And then when you had that, you get d by dt of I omega, and I omega is L. So you can say it's equal to dl dt. But again, that's going backwards. It really, the reality is you should start with this, and then in a special case where I is a constant, then you get I times d omega t dt, which is equal to I times alpha. So anyways, I'll say dl dt where L, and I'm not going to put a vector symbol on this right now. I'm going to tell you why in a second, but where L is equal to I omega, I did that specifically so you can see the parallel. Momentum is P in linear world, and momentum is L in the angular world. And the analog to mass in the rotational world is moment of inertia I, and the analog to velocity V in linear space, its analog is omega and rotational physics. So that's what I'm trying to show you there. Now we can go from this in the exact same way and say if the summation of the torques is equal to 0, then dl dt is equal to 0 vector, which means L is equal to a constant. So that too is conservation of momentum, but in this case, it's conservation of angular momentum. So if you were asked, say, on the final exam, because this course, 241, and the 242 course, and the potential third semester course of this, all of those are really comprehensive courses. So at the end of the second or third semester, we could ask you, under what conditions is linear momentum conserved? And you'd say only when the net external force is 0 or negligible. And then I could say, under what conditions is the angular momentum conserved? And you say only when the net external torque is 0 or approximately close to 0 or negligible or something like that. So that's just something to keep in mind. So now you know basically under what conditions momentum is conserved in the linear case as well as in the angular case. Now, comment about the L equals I omega not being in vectors. It turns out that you can sometimes, and your book handles this, sometimes L is actually parallel to omega vector. So we talked about in chapter 10, we talked a little bit about the omega vector. So if something's spinning this way, you'd say, okay, I'll put my right hand on it and I let my fingers curl around in the direction they're spinning. Then my right thumb points in the direction of omega, the vector. And you do the same thing with omega as you do with L, but L can be, for instance, R cross P for a single particle, where R is a vector that points from the origin to the particle, and P is the mass times the velocity of the particle, and then you do that cross product and you get an angular momentum vector. So you can do all that again, but in this case, the L is not always parallel to I, so that's why I didn't write L vector is equal to I omega vector. If you look at the case where they're talking about specifically spinning top and a gyroscope and rotational imbalance, when they're talking about those sections, you'll see what's going on with that. So I'm going to say C section, let's see, C subsection 11 dash, and let me check this real quick. I want to make sure I get the right section. It is covered in there. So yeah, I'm going to say rotational imbalance. So it's 11-5-1. Rotational imbalance. Okay, so you can sort of always treat the I times omega as the magnitude of any continuous body. So like a top or a football or something like that. You can say, okay, this object's spinning, it has an angular momentum, and that angular momentum has a magnitude equal to the moment of inertia, which you can calculate with calculus, or if it's a discrete collection of bodies, then you can actually use summations to calculate the moment of inertia and then multiply that by the magnitude of the rotation rate about its axis. And that always gives it to you. And then you can use your right-hand rule to define the actual direction of L. It's just not always the case that L is parallel to I. So anyways, we'll cover that. So conservation of momentum just means if the net torque on a system, or conservation of angular momentum, if the net torque on a system is 0 or negligible, then we can approximately say that the angular momentum will be conserved. If it's actually 0, we can say that completely, but if it's negligible, then we can say it's approximately constant. So we just need to keep that stuff in mind in terms of how you calculate the magnitude. So for instance, let's consider an object rotating on a string of changing length. So for instance, this will be example 11-1. And what we have here is, let's say we have a table like this. And in this table is a hole in the middle, and you can pull out a string. And then on that string, we have this right here. This distance is called R1, say. And I'm going to say it is, I don't know, 0.95 meters. And I'm going to say the object is rotating this way. And the velocity, which I'll call V1, let's say that's on the order of 3.0 meters per second. And of course, the string goes through the hole down here. And then you see that I could, in principle, give that a tug. And when I do give that a tug, what ultimately happens is now the string is a little shorter. And the ball on this side, for instance, will be going with a velocity V2 equals question mark. And this time, the radius R2 is going to be equal to, let's say, 0.30 meters in this case. Okay, so we're going to go from 0.95 to 0.30 meters. And I don't even know, we don't necessarily have to have a mass. So I'm going to leave the mass off. Let's just say, obviously, the object has a mass m. So let's assume the ball has an unknown mass, and we're just going to call it m. So normally if I give something a symbol, that means we know it. This is where I'm explicitly saying I'm giving it a symbol despite the fact that I don't know it. And what I want to know is, what is V2? Okay, so our solution can be worked as follows. What I want you to realize is by me pulling the rope up and down, say, okay, all I'm doing is basically reeling the string into the hole, or allowing the string to dole out the hole a little bit longer if I chose to go the other way. And the forces are all acting in a line parallel to the path from the ball to the actual center of rotation. So the net torque has to be by necessity 0 here. So the summation of the torques is equal to 0. I didn't mean to write that in red. So the summation of the torques is equal to 0 here, which implies L equals a constant. And it's technically a vector, so I could put it like that if I wanted to. You can see here that the angular momentum in this case, using our right-hand rule, should be actually pointing perpendicular to the tabletop upward in both before and after. So you can see that the one-dimensional, or excuse me, the vectorness of this is really a one-dimensional thing where L is positive, pointing along what I would maybe call the positive z-axis, which is up, and maybe we'd say the positive x-axis is coming out of the page and the positive y-axis is going to the right. So anybody have any questions on that and how that's set up yet? All right, well, I'll go on. So what I'm going to do is I'm going to say L initial, which, remember, for a particle, L is equal to, and I'll say particle, is equal to R cross P, which equals R cross M times V. That's really what it is. Now, in this case, notice R is supposed to be the vector that points from the center of rotation to the actual object. So in this case, I would say that's my R1 vector, right? And you can see that they're automatically perpendicular. R1 is perpendicular to V1. So I can just say that it's going to be R1 times P, and P is M times V. So I'm going to say this is R1. Oops, didn't mean to write in green still. This is R1 times V1, or times M times V1, which equals 0.95 meters. Let me let the student in. Times 3.0 meters per second times M. And 3 times 0.95 is really close to 3, but it's actually 5 down each time from the 1 meter. So it's going to be 2.85. That's how I turned a multiplication into a subtraction problem using distributive property. So this should be 2.85 meters squared per second times the mass. And I'll just check because, you know, I'm doing this math in my head. There's a good chance that I could make some kind of brainless error. So 0.95 times 3 gives me 2.85. So I agree with that. Now I can do L final is going to be R2 M V2 for the same reasons that it was before. This time R2 is actually 0.30 meters, and M we don't know, and V2 we don't know. So I'm going to write V2 times M. Now I can just say Now I can just say L initial is equal to L final, and that gives me 2.85 meters squared per second times M is equal to 0.30 meters times V2 times M. Notice now that this M cancels out with this M, and I can just solve and get V2 is equal to 2.85 meters squared per second divided by 0.30 meters. So if I take that and divide it by 0.3, I get 9.5. And that works out to be meters per second. So the answer is V2 is equal to 9.50 meters per second. Of course, the 0 is an extra sig fig, so I wouldn't include that in an official answer. But if I were to use that for a subsequent calculation, then I'd want to use that extra digit or more. Any questions on that? So that's one example. Now we'll have another example. Let's say example 11-2. And this one's going to be basically a clutch. And you might not realize this, but in a transmission, you don't have to have as many cogs as you might have thought. And I'm using the cogs in the sense of the cartoon that Meet the Jetsons. Basically, everything was like a wheel with gears on it or something like that. So you might think that if you looked at the transmission in your car, you'd open it up and see a bunch of gears. And there are gears in there, but they're gears to take the rotation of the axis that happens to exist in the transmission and make it at a different rate, a different ratio as to how many turns that axis is turning or the axle's turning versus how many turns the rear axle or the drive shaft is going to turn. So that's the difference, for instance, between first gear and second gear and third gear. First gear takes a very close ratio of the turns coming out of the engine to the turns. Actually, I should say a very small ratio, meaning the turns in the engine is way huge, more large than the turns of the back axle. But as you go to second gear, the turns in the engine say is still about the same, but the turns of the rear wheel is a little larger than it was before. And in third gear, it's a little larger still, and so on and so forth. Those gears can do that kind of stuff. But to actually make a linkage between the spinning of the crankshaft, say from the engine versus, I think is that the crankshaft or camshaft? I don't know. I might be mixing those up. Doesn't matter too much. I'm not a really mechanic, so I miss names. But anyways, the main driving part of rotating thing that's in your engine, which I think is the crankshaft, that's going to come into your transmission and just be spinning. You know, if you look at the RPMs on your engine, it might say 3,000 or 3,500 RPMs, which means revolutions per minute. And that means how fast that thing would be spinning. Well, you're going to have another axle coming out of the back of your transmission, assuming you have a rear-wheel drive vehicle, and that axle is going to turn your drive shafts, which is going to go to your rear differential, which is then going to turn your rear axles. Now, that is not necessarily going the same speed either as the rear axle, because there's ratios and stuff like that can be done in there, but you should have some kind of linkage in between there, so you can take that axle that comes out of the back and put a different ratio for what comes in the front of the transmission versus what comes out of the back of the transmission. That's where the first, second, third, fourth gear comes in. But what really ultimately makes the linkage is you just have two basically circular plates, and they're pressed together kind of hard, but it's just friction holding them together. So you don't actually have to have teeth or anything like that for them to interlock. They can just sit against each other with the same central axis lined up perfectly. When they're sitting against each other and there's enough force between it, the friction between them is going to hold it. So when you push the clutch, what you're doing is pushing some mechanism that allows those two plates, the plate that's connected to the spinny thing from the engine and the other plate that's connected to the spinny thing that leaves the transmission, ultimately the transmission, that just pulls them apart. And then as you let the clutch go, these things fall closer together, and there's some mechanism that forces them together real hard. So that's really what we're talking about here. And in this problem, they're saying a simple clutch consists of two cylindrical plates. By the way, a cylindrical plate has a moment of inertia 1/2 mr squared, whether it's a cylinder that's that tall, it's a cylinder that's a mile tall, or it's a circular plate, that's still a cylinder. Okay, so even just a little plate is fine, and that's what we're talking about here. So they're saying a simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. The two plates have masses. So let's record these masses, for instance. I'm going to say the mass of one plate, call it A, that's going to be 3.0. I think I'll just use two sig figs. I'm going to say 3.0 kilograms. And then I'll say the mass of the other plate, M sub B, is going to be 9.0 kilograms. I'm going to say the radius of A is equal to the radius of B is equal to just plain radius. And I'm not even going to give that. Okay. What I'm going to also say is that the plate A implies that it has an angular velocity initially, let's say omega 1 is equal to, I don't know, let's say 314 radians per second. Okay. And that's 1. And I would say omega 0 is equal to 0. So what we're talking about is, yes, we're going to take this disk with mass MA, and initially it's not going to be moving at all. And we're going to try to figure out, what kind of torque would have to be required to actually make it rotate that speed. And I'm going to say it does all that in a certain amount of time. And I'm going to say that amount of time is, let's say 3.0. Now that's kind of a big time. Let's say delta t is equal to 2.0 seconds. Okay. So what we're going to do is we're going to have this plate spinning, or whatever. And then all of a sudden you pop the clutch, and then that plate is going to attach to another plate. And then that other plate and the first plate are going to start rotating at a new speed, omega 2. And we're going to ultimately figure that out. But the first thing I want to do is I want to figure out the angular momentum L of M sub A. Okay, that's the first part. And then for part B, I want to figure out the torque required. Let's say torque sub A equals question mark. In other words, I want to know what torque would be required to actually cause the angular momentum that we calculate in part A, i.e. that we allow it to go from omega equal omega 0 to omega 1 in a time of 2 seconds. How much torque does that take? And then in part C, what I'm going to do is I want to know, assuming plate B is at rest, so let's say MB initially at rest, omega 2 equals question mark. In other words, we're going to let them two come into contact, and because of their different masses, conservation of angular momentum is going to require something to change about it. So for instance, we have a certain amount of angular momentum. That's what we're calculating in part A. That angular momentum is going to stay constant because we don't have, if you treat the two disks as the system, then disk A has an angular momentum and disk B is sitting still. So the total angular momentum is just the angular momentum of disk A. But then when disk A is in contact with disk B, friction is going to cause them to interact with each other. That is a force, but remember that's a force on one part of the system from another part of the system, and therefore it's an internal force, and therefore you don't have to take that into account. You shouldn't take that into account, in fact. So ultimately, the net external torque on the system is still 0. So with that in mind, conservation of angular momentum can come into play. So let's do this. We'll do solution. So here's our solution. So L1 equals L2. And we'll say for part A, LA, the angular momentum initially, is whoa. Dang it. Okay, L is equal to I times omega 1. So that's the angular momentum we're talking about. We're not talking about before even A is spinning. So we said it's a cylinder, so that's going to be 1/2 times MA times R squared times omega 1. Well, that's 1/2 times 3.0 kilograms times r squared times 314 radians per second. And oh, I should have gave us a radius. Sorry about that. Let me go ahead and include that. So right here, I'm saying the radius is in fact r, and I'm going to call r equal to 0.40 meters. So it's 40 centimeters. That's a pretty big radius for a transmission plate. But either way, we're gonna, or tension plate or whatever, thrust plate. So when I go to calculate this, I can now do the following. So LA is equal to 1/2 times 3.0 kilograms times 0.40 meters squared times 314 radians per second. And that is just by itself, not squared. When I calculate that, I'm going to get on 0.5 times 3 times 0.4 squared times 314. That gives me 75.36, which is 2 extra sig figs, by the way. That's 75.36 kilogram meter squared per second. And again, your book tells you there is no special name for this unit. So we just use kilogram meters per second, and that's LA, the moment of the angular momentum before they come together. I'll make this a little prettier. Okay, so that's part A. Part B, they want to know what the torque is. So for part B, torque, which really it's the total torque, but in this case it's only one torque that exists, is equal to delta L over delta T approximately. It's really supposed to be dl dt, but we're going to assume this is a small enough time interval that we can do the calculation. And the angular momentum before and after, the delta is final minus initial, so I'm going to say that 75.36 kilograms meters squared per second minus 0, and all that took 2.0 seconds. So you can see that this is going to be about 37.518, 37.68. Let's see if I did that right. I'm going to divide that by 2. Yeah, 37.68. That's 2 extra sig figs as well. And that is, if you look at it, it's kilogram meter squared per second divided by seconds. That's kilogram meter squared per second squared. But a kilogram meter per second squared is a Newton. And then you got extra meter, so it's a Newton meter, which is exactly what we expect for torque. So that should be part B. Any questions on that one? No questions? All right, so the conservation of angular momentum part is pretty straightforward. We're basically going to have, for part C, we're going to have 1/2 m(a)r squared omega 1 is equal to, notice it's 2 cylinders, so they had the exact same formula. The only thing that differs now is now that it's 2 times the mass, or it's MA plus MB is the mass. So I'm going to say MA plus MB times R squared times omega 2. I'm running out of room on this here piece of iPad, but I think you can see what's going on there. So ultimately we say omega 2 is going to be the angular momentum that we have first, and then divide it by 1/2 ma plus mb times r squared. So the initial angular momentum is 75. Whoa. Is 75.36. And again, those are extra sig figs. I'll leave the units off because it's getting kind of small. All that's going to be divided by 1/2 of, in this case, it's going to be the 3 kilograms plus 9 kilograms. Again, I'm keeping the units off. And then times the r squared, which is 0.40 meters squared, like that. And that's it. That's the calculation we got to do. So I'm going to take the 75.36 and I'm going to divide that by parentheses 0.5 times parentheses. Actually, I don't need a parenthesis. I could just add those because clearly 3 and 9 is 12. So I'm going to say 0.5 times 12 times 0.4 squared. And that should be everything. And in this case, I get 78.5. And that is radians per second. And that is, of course, omega 2. And that's the answer to part C. Any questions on that? I'm sorry about fitting it in such a small space, but I figured why start the next page if I can pull it off this way. No questions? Everybody follow that? I think that's supposed to be pretty self-explanatory and pretty easy. Okay. All right, well, let's start another one. Now, there's an interesting thing that happens with stars, and I actually did quite a bit of explanation of this in the class, and I wasted way too much time. I shouldn't say I wasted it. I was teaching them stuff. But basically, when a star goes through its life, it's initially what makes it go from a quote-unquote proto-star to a star is that it starts to efficiently fuse hydrogen into helium in the core. And what I mean by efficiently is it keeps doing it on its own. Like one, reaction occurs and then another one occurs and another one. And basically it keeps on doing it as long as it has hydrogen available. And what happens is you have to have a high enough temperature. It turns out to be about 10 million Kelvin. You have to have a high enough temperature for the average kinetic energy of the hydrogen atoms, which at that temperature, they're going to be so hot that the electrons have completely divested themselves of their parent atom and they're running around loose with all the protons. So the protons have to be so fast that they can, despite their repulsion, come close enough to collide. That's called overcoming the Coulomb barrier. In other words, it has to have above a certain amount of energy. As I said, that energy occurs around 10 million Kelvin. So that's sort of the minimum temperature of the core of a star. Our star is around, I think it's 15 million Kelvin, somewhere around there, 15 or 25, something like that. But the main thing is once that happens, then two protons run into each other and this weird thing happens. One proton spontaneously turns into a neutron and it spits out a something to account for the charge that was lost. And that thing that it spits out is an anti-electron called a positron. So that accounts for conservation of charge, but now you've got a proton and a neutron stuck to each other. And then that proton and neutron will find another proton and neutron that's been made the same way, and they're going to collide and some other stuff's going to happen. And ultimately what happens is you get a helium nucleus that is is less heavy than the 4 protons combined. So the 4 protons that came from the hydrogen atom, the 4 hydrogen atoms, has a mass that's greater than the 2 protons and 2 neutrons in the helium atom. And that actually causes, via E equals mc squared, a difference in mass that gives you energy, because you take that difference in mass, multiply it by c squared, And that is the energy that's left. Now, you also have to take into account, positrons and neutrinos and stuff like that that are carrying energy away, and matter for the case of the positron. But those are really small compared to the actual energy and mass of the existing alpha particle, or the helium nucleus. So that's what's going on inside the core of a star. Eventually it'll run out because there's no really good circulation mechanism. So it'll fuse all the hydrogen and the helium, it'll run out, and then the gravity will crush that inner core. That inner core becomes hotter and gets a little bit bigger because it's got to support all the weight of gravity above it. And at that point, the hydrogen that's all gone now has been replaced with helium, and now the helium reaches that critical temperature of around 100 million Kelvin. At that point, you can actually fuse hydrogen into hydrogen, or excuse me, helium into helium to make carbon. And then you start producing carbon. But outside of that core that's now hot enough to fuse helium into carbon is a shell of hydrogen burning to helium. And then that continues. If the star is massive enough, that continues. It'll run out of the fuel in the middle, which is helium right now, and then it'll start burning carbon and some of the other fuels. And it keeps doing that until it gets to iron, and that's the dead end. Once the dead end comes, then it can explode in a supernova, or it can collapse into a neutron star or a black hole. Or if it gets before that and doesn't make it necessarily any further than making carbon in the core, then it'll become a white dwarf. And that's a super hot thing that is essentially a ball of carbon, and it's very tightly packed. Like it's trying to force the electrons into the nuclei of the atoms, and it's only that repulsion force that's keeping it from happening. But in the case of a neutron star, basically it forces all of the electrons into the nucleus. In other words, it overcomes that force that was preventing it from doing it. And basically all the protons become neutrons, and you get basically a star with the density of a nucleus of an atom made essentially of neutrons. And because it's got the density of an atom, it gets really, really small. So it's not abnormal to have a star that might have started off 3 or 4 times the mass of our sun, now has very close to 3 or 4 times the mass of our sun. It lost some, but not too terribly much. But now has a diameter of on the order of 10 kilometers, the size of Washington, D.C. So that's what we're wanting to do. It says, in this case, I'm going to say estimate. This will be example. Whoa, Nelly. This will be example 11-3. I'll say estimate the rotational speed, or let's say the rotational velocity of a neutron star that started with a radius, of, let's say R is on the order of 10 to the 6 kilometers, and became the neutron star with R2 on the order of 10 kilometers. Assume the original star had M on the order of 3 times the mass of the sun, and made 1 revolution every 30 days. So that's our problem. Okay. So in this case, basically, yeah, some matter is going to blow off when the thing, goes through this act of gravity collapsing on the core and all this good stuff. Some of the shells will be shaken loose. There will be neutrinos that might bounce in and out. And sometimes it gets so dense that the neutrinos can actually knock matter loose. But generally speaking, the mass isn't going to change appreciably. And there's no net external torque on the system. So the answer to this hinges on conservation of angular momentum. So L initial is equal to L final. And again, the angular momentum is conserved because there's no net external torque on it. All the forces that are happening between parts of the star, acting on other parts of the star. It's in essentially a vacuum, so there's no real anything to pull any forces on it any other way. So you can't really get any torques. What we have, if we assume that they're actually spheres, then the moment of inertia for a sphere is 2/5 m1 r1 squared times omega1, and that's equal to 2/5 m2 r2 squared omega2 squared. But remember, m1 is approximately equal to m2, which I'm just going to call m. You can already see that the 2/5 is going to cancel out with the 2/5, but now I can see that I have mr1 squared omega1 is equal to mr2 squared omega2. Now we can see that the m's cancel out, and we ultimately get that omega2 is just going to be equal to r1 over r2 times omega1. So omega2 is going to be r1, which we said was about 10 to the 6, over r2, which we said was about 10 to the 1, and it's actually just 10. It's actually just 10 kilometers, but so you could see what the exponent was. I wrote it that way. That's going to be squared, and then all of that times 1 revolution per 30 days. Okay. Well, 10 to the 6 divided by 10 to the 1 would be 10 to the 5th. And then when you square that, that's 10 to the 10th. So that's going to be 10 to the 10th times actually, let's call that 10 to the 10th revolutions per 30 days. So now I can say 1 day is equal to 24 hours. And I can say that 1 hour is equal to 3,600 seconds. And I can switch from revolutions per day now to revolutions per second. Okay, so I've got to take omega2 is equal to, I take 1 e to the 10th. So be careful if you write in e to the 10th, then that would work fine. But if you, well, you just got to be careful. You got to make sure if you're using the EE key or the EXP key, that's normally expecting scientific notation. So you're just getting the times 10 to the power thing. So just be careful with that. In this case, I took 1 e to the 10, and I am dividing it by 30 to account for the 30 days. And now I'm going to take that and divide it by 24. And that brings me to revolutions per hour. And then I'm going to take that and divide it by 3,600. And that gives me revolutions per second. So I get 3,900 essentially revolutions per second. So that's quite a bit faster than 1 revolution every 30 days. And in fact, if this neutron star happens to have one of its jets, and the neutron stars generally have jets that aren't necessarily aligned with their rotation axis, so they're going like this around. if that jet happens to cross our planet Earth, then we will recognize that neutron star as what's called anybody know?
Quasar?
Actually, that's a version of it. Yes, we also call it a pulsar. But a quasar is actually a quasi star that does something like that. So it's a little bit different, but it's essentially the same thing. In this case, it's called a pulsar. There's also magnetars, which means they're highly magnetic, but they're all sort of somewhat related. But close enough. I appreciate that. So notice you got this thing that's revolving at 3,900 revolutions per second. That's pretty fast. And in fact, I believe her name was Rubin, Dr. Rubin. She was it was either a postdoc or a grad student at the time, and she detected this blinking light, and it was very, very consistent, like very high frequency on the order of several hundred pulses per second. And in fact, they initially labeled it LGM for little green men. And ultimately, her PhD advisors won the Nobel Prize for the discovery of it and explaining it, even though she's the one that discovered it and ultimately did it, explain it. But anyways, let's not belabor that horrible sexist point that might have happened. But anyways, the main thing is now she has famously been the first person to identify a pulsar, and we know now that it's that. And in fact, if you watch them over a long enough time, that pulsar frequency does decrease because it is losing energy slowly over time because of the jets. So anybody have any questions on that one? Imagine that, a star that's so big, I'm talking 10 to the 6 kilometers. That's 10 to the 8th meters. So that's basically on the order of a light second, about as far, the diameter is about as big, or excuse me, the radius is about as big as the distance between the Earth and the moon. That'll give you an idea how big the radius is. And then all of a sudden it's about as big, the radius is about as big as Washington, D.C. So you can imagine that's a huge change. Anybody had any questions on that? All right, so that's some of the cool stuff. I will remind you about the angular momentum, not necessarily aligning with omega. And in this case, we're going to have an example where we're going to show conservation of angular momentum with basically like a playground toy or a playground setup, if you will. So if you go out into a playground, you'll often find a big circular disc. It normally has these galvanized metal poles that stick out of the disc and then go up diagonally, and then they run into sort of an upside down U shaped thing. And there's several of those, and they spin really, really fast on the axis. And I highly recommend you go to look up some Tosh.0 videos of some of the horrible things people have done with those. You get to see some serious physics and some serious potential lethality and death. People will take their scooters or their motorcycles and lay them over on their side, and then get a bunch of people on that little merry-go-round set up and let the motorcycle or the scooter spin it so fast that you couldn't do it with just running. And then people start flying off like it's Sim City or something. It's kind of wild to watch, as long as you assume that no one's hurt, which is not necessarily true, but it just makes me not feel horrible for seeing this mayhem going on. So let's look at another example. So this example, and I've got to take it off of that automatically correcting my drawing stuff. This example I'm going to call 11.4. Okay. So in this case, let's imagine a circular platform. So we have a circular platform like this, and it's sitting perfectly still. And we have a person sitting on it who's perfectly still as well. And this person has a mass of 60 kilograms. Okay. Let's say this disc, this ride in the playground, actually has a mass equal to, let's say, 200 kilograms. And I'll say 200 with a decimal point so we can pretend that has 3 sig figs. And let's say the radius of it, I'm going to say the radius of it is, I don't know, let's say 4.0 meters will be the radius. And essentially, we've taken off all the rods. Remember, it normally had like a pole that came up like this and turned off that way. And then that pole was connected to a pole that came around this way and then went down there and then came around this way and went down there. We took all that off. So this is just a circular plate and we can treat it like such, in which case it's a cylinder. So what we know is initially the person is sitting still and the disc is sitting still. So initially, person and merry-go-round are not moving. Then the person walks tangentially. In other words, he just walks along the edge of the circular disc, basically. At, let's say 5.0, nah, 5 is kind of fast. Let's say 4.0 meters per second relative to the ground. How fast and in which direction does the disc rotate? So that's the problem we're trying to solve here. Let's say solution. So again, we have the summation of the torques is equal to 0 because we're assuming frictionless. So it's approximately frictionless. So that implies the net torque on the system is equal to 0. And we say, therefore, L initial is equal to L final, but L initial is equal to 0. Yes, Brandon.
Even though it says tangentially, wouldn't there still be a direction, like a clockwise or counterclockwise in the direction he's walking?
Yes. And what I was doing with that was I was actually imagining that this guy was walking into the page, but that was completely in my head. And I didn't tell y'all anything about that, which I say is really y'all's mistake, not mine. No, you're actually right. Yeah. So what I'm doing is I'm going to say the person is walking into the page. So if you're looking from above, that means the person's walking in a counterclockwise rotation. Does that make sense for you?
Yes.
Thank you for calling that out. I was totally just thinking that in my head and literally didn't tell y'all. So that's all on me. So now that we have that, remember they were initially sitting still. That's why I said the initial angular momentum is 0. But now what we have is this. We have 0. Oops. We have 0 is equal to, now we've got a circular disc. That moment of inertia is 1/2 times the mass, which is 200 kilograms, times the radius, which is 4.0 meters squared, times, now they're both going to rotate at the same speed. That's the, oh, actually, no, it's going to be angular rotation of, what did I call that? The disk. So I'll say omega d. And then we're going to have plus Now, for the person, since the thing is like 4 meters in radius and therefore 8 meters in diameter, that's good, 26 feet or whatever. A person being a couple feet wide is pretty insignificant compared to 26 feet. So we're going to treat this person like a particle, in which case their moment of inertia is, or excuse me, their angular momentum is just the distance they are out, which we're saying he's walking on the edge. So we're going to say R times his mass, which we have, times his velocity, right? And this is the velocity relative to the ground. So I'm going to say, in this case, we have 4.0 meters times the mass, which is 60 decimal point kilograms, times the velocity, which we said was 4.0 meters per second. Notice again, it's relative to the ground, not relative to the disk. Okay. So that allows us to solve for omega d, and you see that it's negative. I will put here that this is CCW from above, which I already wrote once, but I just want to remind you that. So now what we see is the omega of the disk will equal 4 times 60, that's 240, times 4, that's 960. So that'd be 960 kilograms meters squared per second. And now I've got to divide that by 1/2 times 200 times 16. So that's 1600. And that's kilograms meters squared. So ultimately what we see, and I'll test my calculation here. I'm going to do 4 times 60 times 4 just to make sure I got it right. 960 was right. Now I'm going to take that and divide it by, I'm going to test my math again. I'm going to say 0.5 times 200 times 40 times 40, close parentheses. And that gives me 0.0060. Notice everything cancels out except for per second. That means it comes out in radians per second. Okay. And the answer is actually going to be negative, by the way, which tells us it's going to be in the clockwise direction. So that's our angular speed, and we could say v disk edge. So if we wanted to know how fast the tangential edge is going, that's just r times omega d, which is 4.0 meters times negative 0.0060 radians per second. So in this case,
I think that should be 0.6.
Thank you. Let's try that. 960 divided by 1600. That's right. I'm wondering if I calculated my other part wrong.
You put 40 squared instead of 4.0. That's what gave you the small.
That's what it is. Thank you. Appreciate that. Excellent. Good catch, man. I can't tell you how much that helps when y'all do that. I've been having a lot of people catch my little errors lately, and that's been super, super helpful. So yes, it's going to be negative 0.60 radian. I did think that was kind of small, but I was like, oh, well, the calculator told me, I'm just going to trust it. No, that's not what we're supposed to do as physics students. But anyways, I did do it. I'm a loser. 0, and that's radians per second. So when I multiply that by 4, you can see that's going to be 2.4 meters per second. So I will say the answer is and this implies, this negative implies it would be clockwise from above. Okay, so that's the angular speed. And then if you want to compare how fast that is to the person, clearly the person is a lot less of a momentum issue than the disk is, and that's because the disk is 200 kilograms. Therefore, the disk is rotating only at a 2.4 meters per second at the outside edge, whereas the person is revolving at a 4.0 meters per second clip, like that. So now I'm going to take this, box it off, and say that is the velocity of the disk at the edge. Any questions on that? All right, well, yeah, I think I should go ahead and get another one in here. So there's a neat one your book is doing. Actually, all of these I'm doing somewhat parallel to your book. I'm just making up the numbers and sort of remembering them off the top of my head, but they're essentially the same examples, just entirely different numbers because I'm not even taking time to look up the numbers. So let's look at example 11.5. So example 11-5. In this case, what we're going to have is an instructor, let's say, holding a bicycle wheel. And this is not that easy of a thing to do, especially with me with my bad shoulder right now. I could seriously get hurt. But if you imagine the person sort of holding the bicycle wheel like this and it's spinning very, very fast, but you're also putting the person on their own merry-go-round, then and nothing's moving right now except for the wheel rotating. Let's say this wheel is rotating this way. Okay, that means the angular momentum, which I'll use a green vector for, is that way. Okay, whoa, wait a second, I drew that backwards, didn't I? Yeah, sorry about that. Good, I didn't want it to have to point down anyway, so that works out better for me. So I'm going to say the angular momentum is pointing up, and that's using my right hand rule. So the wheel is spinning this way, therefore my angular momentum's up, and that's the initial scenario. Now what the person's going to try to do is the person standing on this frictionless turntable is going to try to flip the bicycle wheel over the other way around. So now they're going to try to take that disc. He's still going to be standing on that disc, only now he's trying to turn this wheel the other way around, so he's going to have to actually flip it. So that's not the best drawing with his arms. I think he might have suffered a bad injury or something in this whole process. Oops, I don't want his legs to be black. I mean blue. I want him to be black. So now what's going to happen is the disc is spinning the opposite way, like that. And that means now the angular momentum is this way. Okay. But conservation of momentum is not going to just allow that to happen. Okay. So what's going to happen is now what we have is conservation of angular momentum. And what I'm trying to figure out is what's going to happen and which directions are those things going to happen or like that. So let's work it out. We'll say the net torque is equal to 0. That implies that L initial is equal to L final. And L initial is just equal to L. as we have drawn here. But L final is equal to L2. And in this case, it'll be plus L turntable. So I'll just call it TT. So the L of the turntable. So if I set these two equal to each other, what I get is L I is equal to LF gives me L is equal to L2 plus L turntable. Now, L2 is just equal to the negative of L1 because I just flipped it over, right? So if I plug that in to here, I'm now going to get L. Actually, I shouldn't have called that L1. I should have just called it plain L. So let me erase that. So I'm now going to get L is equal to negative L plus L turntable. That gives me that 2L is equal to L turntable. So what we see is that now, because I've turned the instructor or whatever has turned the wheel upside down, that means the disc is going to have to rotate the original way the wheel did, and it's going to have to do so with twice the angular momentum. So this implies the turntable will spin the same direction as the wheel originally spun. And its angular momentum must be, let me go ahead and write it as a word, twice the angular momentum the wheel originally had. Now, of course, the turntable is likely to be a lot heavier, obviously, and the turntable, by necessity, is going to include the human that's holding it. The human's quite a bit heavier than the wheel, so all of that's going to result in basically the wheel moving, the turntable moving quite slow relative to the wheel or compared to the wheel. So, but the main thing is we see that it will actually rotate in the same direction. So I will draw it like this. And now the angular momentum of the wheel, which I'll draw this way, or the turntable, excuse me. That's L turntable is like that. And that equals 2L. Any questions on that? All right. Well, that gives me about 4 minutes left, which really isn't enough to do another example. So I'm going to leave it at that. And next time we will start on, actually we'll start in section 11 dash. I don't have to do 11.2. That's why I'm stammering a bit here, because 11.2 is the vector cross product being introduced. I've done that like 2 or 3 times already. So we know already that torque is equal to R cross F. I'll just reiterate that since I got a little bit of time. So I'll say, let's put this line across here to break it up. So torque, whoa, Nelly. Torque is equal to R cross F. And what I mean by that is, like, if you're trying to turn a hex bolt with a wrench, say, and you apply a force, let's say this way, then the vector R is a vector from the center of rotation to the point of application of the force. And in fact, if you extended this, this would be the angle theta. And what you'd say is the magnitude of the torque is equal to the magnitude of the radius, or the R vector, times the magnitude of the force times the sine of the angle between them, which is also just RF sine theta, which is also R perpendicular times F, which is also F perpendicular times R. All of those different things work, but the other thing is that torque is actually equal to that R cross F. We also know that angular momentum is equal to R cross P, and we've already done all that calculations of showing you how to use the determinant to calculate those. So we're good to go. You guys are free to go. I will wait till the last person leaves, and in case anybody has any questions. So have fun, have a safe weekend. I will see you guys next week. Don't forget to start on your test and practicing for your practice test. I mean, for your test.
I had a question.
Yeah, for sure. What's up?
My mic on?
Would you like me to stop recording or anything like that?
Oh no, I had a question on one of the practice tests.
Okay, go ahead.
It was part 2, chapter 3 and 4.
Okay. You wanna do you wanna take the screen over and show it up here? Or do you not
I
have it?
don't think I know how to do that. I think we tried that last time, but it
Okay.
says
I just turned it where you can if you want to. It's just a matter of whether you figure it out. Otherwise, you have to read it, or I'll look it up or something like that. But if you can give me roughly what the problem is, I might can help you. I should be able to help you. You said
okay.
it,
I'm trying to look at it.
go ahead. You said, was it a practice test you were taking?
Yeah. Oh no, it's it says that it was missing or whatever. That's what I was saying. Can you make it available? But
Oh, okay, gotcha.
it's part 2, chapter 3 and 4. But it says, I guess my computer won't allow me to share my screen, so it's my
Gotcha.
computer thing.
So you're talking the actual practice test PT02 chapter 3-4 under the module it says practice test. Is that what you're talking about, Richard? You're muted right now. I don't know if you said it.
Yeah.
Okay, so it is that practice test. Well, the practice tests don't count against you or anything, so there's no need to do that. Did you do test 2?
Yeah, I did test after that, so it's the same exact thing.
Yeah, well, it comes from the same bank that I make the test out of, but I don't allow people to take the practice test after they've done the test already, because that's the whole point of the practice test, is so you get a better grade. I'll pull up the
Okay.
grades and just see if there's anything missing test wise that I might want to address. Let's double check that. And I'm not sure.
Nah, I did all the tests. It's just that one. But if it's not really necessary, because I did the test after that, so.
Gotcha. Yeah, if long as you had attempted it at all, then it's going to help you with that extra credit stuff. But if you didn't attempt it at all and then you took the test, then you just don't get a chance to get credit for it, because you're supposed to do it before the test.
All right,
It
and
looks like you got all the
so
tests handled.
my lab, it's certain ones just conceptual extra credit and stuff like that. Do we need to do that too, or grade?
Yes, the conceptuals count as part of your homework grade. I think it's like 5% of the course grade, whereas your homework's like 10%. So it does count. It just counts about half as much as your regular homework.
Well, I'm saying it's certain ones that say extra credit. Like
Oh, yeah.
it was.
Those
Do
are
we need to do
completely
that or?
up to you as extra credit. So you can do them, but you're not required to. What it does is every one you do, if you get like a 80, like a 75 or better, I'm going to give you 100 for that. And that'll replace any grade lower than 100. And I'll drop one grade more. So like I'm supposed to drop one homework grade throughout the semester. But if I've got, 12 extra credits, then I'm going to drop 13 grades total, but you'll have a 0 for it if you didn't do it.
All right, and there's got one more question. It's I did extra credit like earlier last month. It was like the 8th of October. It was like some assignment.
Let me
Are
look.
you gonna grade that one? It was the extra credit.
Yeah, I might have graded it for a bunch of people already, and then you turned it in. I'm looking for the assignment right now, but yeah, I'll definitely grade it. And if we get towards the end of the semester and you see that I never put oh yeah, I see it now. Yeah, that's what happened. I had a couple people turned it in and I graded. I just hadn't graded yours yet. So yeah, I'll do that. No big deal on that one. I did notice that you missed the first face-to-face test, what we call TO3 chapters 1.
Yeah, I already made it up. You gave me
Did
the
you make it up?
lockdown browser.
Oh, okay,
Yeah.
gotcha.
That was
That's
like
probably
later.
in a different category. I just got to cross that over so it'll help your grade. So
Yeah.
let's see if I can find that right quick while I'm here with you. That's not it. That's not
I
it.
just took it like last week since.
Oh, okay, that's what I remembered your name, so I knew there was something that happened. I just got to find it. That's not it there. That's not it there.
Hold on, I'll help you find.
Yeah, I'm just trying to find it on the grade book. I know I had a different name for it, and I just got to put that in for yours.
Done on October the 29th.
Gotcha.
That's what you needed.
Yeah. Oh, there it is. Okay, yeah, I got you now. I just found that it was just in a different place.
It was imported assignments.
Yeah. Yeah, I can fix that now. So you'll be golden. Anything else, bud?
And the one that I did on October 8th is still gonna be graded.
Yeah, I
extra
just got to
credit
put
too.
that in.
All right.
All right. And actually, there's a couple other students I need to too. So that's cool. Well, thanks for starting. I appreciate that. And I'm putting it in right now. As soon as I can find it. There it is.
All right. Thank you.
No
Yeah,
problem.
man,
It's
that-
in there now, so that should count. And you have a good one, man.
Thank
you. Bye-bye.